So, in these set of lectures, we will discuss the basis of particle detectors. So, we will discuss the interaction of charged particles with matter and then the interaction of neutral particles with matter. So, these are the first two lectures, and in the third lecture, we will discuss actual detectors together with some basics of electronics and data acquisition and so on. So, charged particles lose their energy when they move in material substance, and at low energies, when you have heavy particles, by that I mean particles with a mass of the projectile much larger than the mass of the electron, which is the lightest charged particle. So, that includes, for instance, the muon. We consider that to be a heavy particle in this discussion. So, these particles at least at low energies, and we will see what is that energy, has a characteristic range to it. So, they keep on going depending on the energy and depending on its charge. For instance, an ion of carbon 12 can have a maximum charge of 6, so it can be a charge 6. So, then the characteristic range will of course depend on the fact that it is carbon and also on its energy. At high energies, what happens is, and that what do you mean by high energy? Roughly of the order of half a GeV, the energy loss by ionization sort of competes with the processes which lead to hadronic showers. So, at low energy, the primary mode of a charged particle losing its energy is by exciting or ionizing the target atoms or molecules, as the case may be. So, we define a stopping power S, which is the energy loss per unit distance. Now, that distance can be really in terms of length, or it could be a areal mass density. This arises from three sources. As I said already, ionization is an important, the most important process at low energies. Of course, at very low energies, something else comes in, which is Coulomb scattering of the nucleus. This dominates at low energies. Of course, ionization is also there, but at very low energies you cannot even excite the atom. So, then the only way it can lose its energy by scattering. Then there is this for light particles, especially at sort of moderate energies such as the electron, then you have radiation which causes the charged particle to lose energy. And this is goes by the name of Bremsstrahlung. It's a German word for braking radiation. So, when any charged particle accelerates or decelerates, then it can lose energy through radiation. It can emit a photon, and that is how you can lose energy for especially important for light particles. Of course, it also plays a role for heavier particles such as the muon, but at much higher energies. So, for instance, for electrons of about 10 MeV or higher energy in a lead target, Bremsstrahlung becomes the dominant mode of the particle losing its energy. Of course, this 10 MeV becomes higher of the order of, let us say, 100 MeV for carbon, for instance. If carbon is the target, then muon will lose or an electron will lose energy by Bremsstrahlung at a much higher energy. Okay, so there is a very beautiful derivation, a semi-classical derivation due to Niels Bohr, and I mean there is no time to go through this derivation, but I will give the reference, and it gives a very physical picture of how the heavy charged particle loses its energy by transferring part of its energy to the electron. So, basically the electron recoils against the heavy ion or the heavy projectile charge, and then the semi-classical calculation involves putting bounds, the upper and lower bounds for the maximum and minimum impact parameters, and then semi-classical way of doing it involving a little bit of quantum mechanics and so on. And so, the derived stopping power, the electronic stopping power, which in this case is ionization, is basically given by this expression here, and is proportional to the mass of the projectile, the z of the projectile squared, and inversely proportional to the energy of the projectile. Of course, there is a small logarithmic dependence also. There is a logarithm of beta gamma times me Vp squared and so on. But of course, in the domain where beta is close to 1, gamma is much larger than 1, then these semi-classical approximations become less valid, and you have to actually go to the quantum mechanical and relativistic, fully relativistic quantum mechanical calculations. Okay, so the important takeaway from this formula, and which holds for a very broad range of low energies, is that the energy loss or the stopping power is proportional to the mass, proportional to the Zp squared, and inversely proportional to the energy. In the quantum mechanical case, then this becomes the same kind of leading dependence, but then there is a logarithmic term which goes like gamma squared times mp Vp squared by IE, where I is the typical excitation energy of the electrons in the target atoms. A fully quantum mechanical treatment due to Hans Bethe and Bloch, which includes also the density effect. As the particle moves faster and faster, there is a dilatation in the space, and so there is an increased density that the particle sees, and shell correction, because of course target atoms have atomic shells. So if you include all of that, then the quantum mechanical expression is essential. This is a prefactor, but as you can see, the leading dependence is the same. It is Zp squared by beta squared. In fact, if you go to the expression Ep by Mp, take Mp in the denominator, then you just get a V squared, and this is exactly what it is. So it's a beta squared. Beta squared is just proportional to the velocity squared. Okay, and then of course there is a logarithmic term here, and then a delta, which is the density effect, and then the C by Z, which is the atomic shell effect. And each of these terms, beta gamma are the standard relativistic factors. Beta is just V by C, gamma is 1 by square root of 1 minus beta squared. Vp, the velocity of the particle, is just beta C. Ne is the electron density, Re is the classical electron radius, E squared by mc squared. Avogadro number Na, the target density rho t. This is the mean excitation potential in this case. So it's in principle you can have also excitations of the atom or molecule apart from ionization, and then these have the standard denotation. This denotes the standard mass, atomic number, and the energy of the projectile. Zt, At are the atomic mass number of the target, and of course this we have already said that this is the density effect and atomic shell parameter. There is another parameter here which comes W max. This is the maximum energy transfer that is given by this expression, but for cases other than the electron, then Me by Mp is very small, so you can neglect these two terms. So it just becomes 2 MEC squared by gamma into gamma squared beta squared. And again, in the relativistic limit, beta is close to 1, whereas of course for smaller values of velocity, then you have to take into account beta squared. And then there gamma is almost 1. Okay. So the density effect arises from, of course, the polarization of the medium, because the projectile has an electric charge, it polarizes the medium, and then this shields the field and reduces the effect on the far electrons. Okay, so this leads to a reduction in the stopping power. These are the two key references, one due to Jackson, one the classical electrodynamics textbook of Jackson, and this paper. This is, I think, a kind of must read if you want to look at the semi-classical. It's a very physical kind of picture that you get. And Niels Bohr, by the way, had been interested in this problem much earlier than this basically review was written. He was interested from the 1910s and so on. Okay, there is a very useful tool which is a piece of software written by Ziegler and colleagues, and there are two programs SRIM, which is basically the stopping power for heavy ions in matter, all kinds of matter. You can have elements, you can have compounds and so on, gaseous, liquid, whatnot. And TRIM is the one where you calculate the transmission through these stopping materials. Okay, and this is based on experimental data, so it's very, wherever there is data, he would take that data, parameterize it and then extrapolate it. And this is the website, he keeps it up to date and so on. Okay, so this figure you must have seen earlier, but this is just for recollecting what we just said. This is taken from the particle data handbook, particle data groups volume. It shows the stopping power for the positive muon in copper. So you can see that at very low energies, this is actually a beta gamma factor. So at very low velocities, you have a rise in the stopping power, then a maximum, and then a fall which goes roughly like 1 by E, and then it reaches a minimum, and this is called the minimum ionization, minimum ionizing particles. So you use this term, this jargon, MIP, minimum ionizing particles. So at this energy, you have the minimum ionization, that is roughly between 1.5 and 2 MeV per gram per square centimeter. And then it slowly rises, which is the relativistic effect, and at some point the radiative losses become important, and so this happens, for instance, at this place. This is of the order of beta gamma being about a few thousand, 3,000 or so. Okay, and the energy would correspond to something like a few hundred GeV by C. Okay, now we'll talk about, of course, this is applied everywhere in nuclear and particle physics, but as part of all the simulations of detectors and so on, we will just talk about three simple applications, namely what is the range for a charged particle given this kind of formulation of the stopping power, what is the stopping time, and this is useful in, for instance, estimating the lifetimes of excited states in nuclei, but an analogous technique is also used for measuring lifetimes of decaying particles, and then the a method to identify particles through the identifying the Z, A and E, using these to identify the delta E telescope. So you have a thin detector and you have a thick detector, and you get bands in that, and we'll see how you can identify each of these Z, A and E. So okay, as far as range goes, now as I said, this is true of course for energies below 400 MeV per nucleon or so. So for low energy heavy particles, the range is basically just an integral over the stopping power. So it's dE by S of E, and if you take out the constant k, then the leading dependence is just e to the power of 1 by alpha. Now from that formula, alpha should be 1, but in practice, because there is a logarithmic term, so it gets slight, you can approximate that dependence through a alpha which is not exactly 1 but slightly less than 1. So for particles such as protons to heavy ions, this alpha is of the order of, I think there is a typo here, this should have been 0.6 or 0.8. Okay, there is a typo, we'll correct it in the final slides. So this goes like the range is proportional to e to the 1.7 roughly, in a sort of limited range of energy. Typically, therefore, a 10 MeV proton and stops in about 710 micrometers of silicon, and of course the spread in the range is of the order of 33 microns. Whereas a 120 MeV carbon 12, you can see it's 12 times more energetic, but because its M and Z are both large, then it stops in a smaller distance, 245 microns of silicon. And as you can also see, this the spread in the range is somewhat smaller than the spread in the range for the proton. Proton is lighter than carbon. This is one of the reasons why this spread is somewhat smaller. Now, just to show you the actual picture in a cloud chamber. Cloud chamber is one of the early particle detectors which we saw in some of our earlier lectures. So, this is a cloud chamber photo of a 5.3 MeV alpha from a alpha source 210 lead. So, it actually starts out somewhere here, it propagates in the cloud chamber, then there is a scattering at 2 and then again at 3. So, this is roughly the range of this alpha particle. Okay. Of course, after, if you take into account that the fact that it has lost a little bit of energy through collision here. Okay. Now, as I said, we will also talk about stopping time. So, one can again calculate the stopping time as the range by the effective velocity of the particle, and you can approximate it, and you can get a e to the 0.5 plus alpha dependence. For uniform deceleration, this is about 0.5, whereas in reality it is actually closer to 0.6. So, it's actually the time is proportional to roughly E. It turns out that for 10 MeV protons in silicon, for instance, the stopping time is of the order of 26 picoseconds. Now, this is applied, as I said, to measure the lifetimes of excited states of nuclei, and so this is called the Doppler shift attenuation method for measuring the nuclear lifetimes. And the heavier nuclei, of course, stop faster earlier, their energies are also smaller, so it takes less time for them to stop. So, these range in the energies of interest in low energy nuclear physics, where you deal with about 5 MeV per nucleon collisions, of the order of 10 femtoseconds to 10 picoseconds. So, these excited nuclei which result from nuclear reactions, and then the momentum conservation tells you that the compound nucleus or the residual nucleus should recoil into a backing, into some stopping material, and high purity germanium detectors, which we have not yet discussed, but they are high resolution detectors, typically with resolutions which are sub 2 keV at about 1 MeV gamma ray energy. They are used to, they are put at various angles, and they measure the angle dependent Doppler profile. So, you can see that these are true transitions in this case in 32 phosphorus in this particular reaction. So, 16 oxygen impinging on a 18 oxygen target, and then through a NP reaction it goes here to excited states, and then you produce lots of gamma rays, and some of the transition, two of the transitions are shown here. So, if you look at the forward angle, then you have a distribution of gamma ray energy at higher energies, higher than the so called stopping peak. Once the recoil nucleus stops, then there is no Doppler shift, and this is the peak that you get. But if it decays while it is moving, while it is stopping, which is sort of in this period, the stopping time is of the order of a fraction of a picosecond or a little longer than that, then you get a profile. So, at the early stages of the recoil, you produce gamma rays of this energy. As it slows down, you produce gamma ray energies of lower energy, and then ultimately when it stops, you get the stopping peak. So, you can put this detector at various angles, and you will notice that the profile changes, and then you can fit this to extract the lifetime, because you can you know roughly the, or you have at least fairly good estimates of the stopping power of the recoil ions in the material that you have into which it is recoiling. You can also see that at 90 degrees to first order, the Doppler shift is 0. When you go to backward angles, of course, you have lower energies, and this sort of picture reverses. Okay, this is shown for one transition, this is shown for another transition here, and of course, you can see that the lifetime here obviously is shorter than the lifetime here, because you see much more of these Doppler shifted photons as compared to the stopped photon, stopped recoil emitting the photons. This is the reference. So, from this data, for instance, it was shown that the lifetime of these is 616, but because of errors and so on, there is only an upper limit on this particular lifetime. It could be very short, it could be of the order of even 100 femtoseconds and so on. And these are the error bars, 10 to 15%. Okay. So now let's look at a delta EE telescope. What is a delta EE telescope? Let me repeat. Delta EE telescope is one where you have a thin detector and a thick detector. So the thin detector gives you a signal which is proportional to the stopping power, or which is at least related to the stopping power, whereas the thick detector stops the particle. It loses all its energy in that. So it has lost part of its energy in the thin delta E detector, and then it loses the remaining energy in that E detector. So as we saw, the delta E is proportional to mz squared by e to the alpha, where e to alpha is of the order of 0.7 or 0.8. And so this is a picture taken from this paper. This is a reference. Helium-3 on 232 thorium. So you see bands corresponding to protons, deuterons, tritons, helium-3 and helium-4. Of course, you don't see heavier particles because that would involve small cross sections for picking up particles from the target nucleus. So as you can see also, it is easy to identify the different isotopes of hydrogen. P, D, T are very clearly separated. Of course, so is helium-3. The situation is not that clear when you go to heavier and heavier ions. So if you want to, for instance, discriminate between 28, 29 and 30 silicon, it becomes much more difficult, because then the mass is only differing by 1 part in 30. So then the resolutions of these delta E detectors come into play. However, it is easy to separate different atomic numbers, and that is because of the Z squared dependence. The isotopic thing is a little more difficult for heavier ions. Lighter ions, of course, it is possible, as we saw here. Heavier ions, it becomes a little difficult because it is linear in the mass, whereas in charge it is proportional to Z squared. So it is easy to separate different atomic numbers. If you have a large range of ionic species, also a large range of energies, then in fact one can use 3-element telescopes. You have a delta E1, delta E2, and then a E detector. Okay. I'll just give two very quick estimates using the Bethe-Bloch electronic stopping power. So, of course, for the minimizing particle, we saw that the energy loss is of the order of about 1.5 MeV per gram per square centimeter. Now, it turns out that 1.5 to 2. So, in iron, if you estimate the energy loss for a certain plate thickness of iron, and I have of course chosen this because we were working with a prototype iron calorimetric detector for neutrinos, so there we had used 5 centimeter plates, but this is just an example. I mean, it could be any other material, any other thickness and so on. So, for instance, for this case, the delta E is of the order of about 80 MeV if the muon travels exactly perpendicular to the plate, and if you have 12 such plates, which is what we had in the prototype mini iCal detector, then you lose about 1 GeV. And this is to be compared with the cosmic ray muon spectrum, which of course extends up to very, very high energies. But since it's a power law, the spectrum of cosmic muons goes like e to the minus 2 point something, 2.5, 2.7. So then the low energy muons stop in the early plates, in the first few plates, whereas the highest energy muons penetrate all 12 plates. Of course, in this particular prototype iCalorimetric detector, we had so-called resistive plate chambers, gas detectors, using glass sheets to form the electrodes, and they were in between consecutive iron plates. So you had sandwiches of iron plate, RPC, and so on. So now these RPCs have gas at about 1 atmosphere, but only 2 millimeter gap. So if you, and they had mostly freon, let's say, they had some other gases also as a mixture, but let's consider only freon. Then you can calculate how much is the energy loss, and that turns out to be about 2 keV. Given that the ion electron pair needs about 40 electron volts, for creation of a ion electron pair, you only have about 46 electron ion pairs. Okay. So, you need of course amplification of this number if you want to get a measurable signal. Okay, so there are of course fluctuations in energy loss in the range and in the angle, and these can be estimated within both the Bohr theory as well as within the Bethe-Bloch theory, and one estimate of that was given by Landau. And so you have things called a thick absorber, where the mean energy loss is much larger than the maximum energy loss to an electron, and this is then it's called a thick absorber. You have a Gaussian distribution in the energy. If this is much less than about a percent, then this is called a thin absorber, and then the Landau formulation kicks in. And of course, Vavilov and Simon had a paper on this, where they bridge this gap between the thin and the thick absorbers. There is also a Bohr estimate of the fluctuations, energy loss fluctuations, and which is extended for relativistic particles. As I already said, there is range straggling, and so the stopping of a heavy charged particle is defined by the range, but also by the fluctuation, because after all it is a random process, and of course a large number of these scatterings take place on electrons. So of course both inelastic and elastic, and so therefore you have a spread in this, because there is a statistical spread. And this range straggling of course is more for light ions, as we saw to some extent when we compared the range and this range straggling for protons and carbon 12 ions. There is also angular straggling, and this is given by this expression. This again can be computed through the Bohr theory, but also in the quantum mechanical theory. There is also another parameterization which is quite convenient to use, whereas you have a Gaussian distribution in theta, and then the sigma parameter associated with this Gaussian distribution is about 14 MeV divided by beta times Pc. Pc has the units of energy, so the energy cancels, and then basically a root of thickness dependence when thickness is measured in terms of the radiation length. We will come to that radiation length in the next lecture. Basically, I could define it here. Radiation length is that length in which in an electromagnetic shower the energy gets reduced by a factor 1 by E. Okay, now we come to energy loss of electrons in matter. So we started with heavy particles losing energy in matter, now come to electrons, and the basic two differences are that the projectile is identical to the target electron and that the ME is small. So Bremsstrahlung processes are important. This was not so for heavy particles, at least at low energies. So the collisional energy loss is given by this, and this is a very complicated expression. I have just written it for completeness sake. There is a small difference between electrons and positrons, and the total stopping power is of course collisional plus radiation. And the energy, I have not given an expression for radiation. This is even more forbidding expression. The energy at which these two contributions become comparable is given by a very simple empirical fit, which is 800 MeV by roughly Z. Okay, this is where these two contributions become equal. So you can see that when Z is of the order of 80, as is so for lead, this is about 10 MeV. If you take carbon, then this is of the order of 130 MeV. This is the fractional energy loss per radiation length of positron and electron in lead. You can see as a function of electron energy, right, from 1 to 1 MeV to 1 GeV, the energy loss in units where the length is measured in units of the radiation length, and there is a 1 by E factor here. The electrons and positrons, the d by dx comes down with this 1 by E factor of course, and these are the contributions due to Mollier scattering, Bhabha scattering for the case of positrons, and of course there is a small contribution due to positron annihilation as well. And so on this scale is the thickness. So as you can see in lead, Bremsstrahlung kind of takes over after about 10 MeV of the electron energy. The radiation length, I would just like to say, is of the order of about 6.4 gram per square centimeter for lead and about 43 gram per square centimeter for carbon. I should have mentioned also the radiation length is the, I'll repeat, is the distance in which a high energy electron or positron loses energy to about 1 by E of its value. So, of the order of about 38% of its value. And for the photon, this is of the order of 7/9 of that. Okay, one just small point that when you consider low energy electrons, there is also something called the backscatter of electrons, and this is important when you look at let's say the spectroscopy of conversion electrons in nuclear physics or low energy electrons in general of the order of between 0.1 and few MeV. And so this backscatter coefficient, the number which backscatter as compared to the number which is incident, is of course increases with the Z of the material. It's about half for gold and it is about 14% for silicon for normal incidence. Of course, this changes if you have at steeper angles. Of course, it will this fraction will increase, and of course, it drops off at about half its value at 6 MeV or so at higher energies. Okay. So, in summary, we have talked about the stopping power of charged particles in matter, heavy particles initially and then electrons. Of course, the same thing is true for positrons more or less. Then we have talked about the energy loss in thin targets and fluctuation, just mentioned it actually. Then stopping range and fluctuations in that, both in not only range but also in angle. And then finally, we have talked about electron stopping in matter. Okay. Thank you.